Vanakkam, Subramanian here. In today's section, in today's session, we are going to see the thermodynamic theory part, out of which we are going to cover these aspects, namely first law, then thermodynamic properties of pure substances. That is these two topics of the GATE syllabus. In these three contents, what is it? Basic concepts, BVT, behavior of pure components, and first law of thermodynamics. Okay, in the basic concepts, we need to know about the types of system and surroundings. So the types of system. Okay, what are the types? Three types we'll have. We have open system, closed system, and another one which is isolated system. So there is no this is about the interactions happening between the system and surroundings. So interactions happen between the system and surroundings in the form of mass exchange or heat exchange, or both are getting exchanged. Say, for example, open system allows mass exchange as well as energy exchange. Otherwise, what is called as a pipeline, which is there is a flow. This is a simple, nice example of open system. And closed system. In the closed system, already there is a mass confined. Only this energy interactions are happening in the form of work or heat transfer between the system and surroundings. And isolated system doesn't allow any kind of transfer. Otherwise, it is how to consider an isolated system. It's a insulated container, and always rigid and insulated container. To the rigid insulated container, there is no energy interaction between the system and surroundings, and also there is no mass interaction. For each and everything, better to know the examples. No, here isolated system is a rigid container, insulated container, which is a isolated system. And closed system, vessel closed, which is already closed, and we don't add any mass during the process. And energy interactions in the form of work and heat both are happening. Open is a thing allowing all kind of transfer. So in industrial practice, in a continuous process, we have this open system. So whatever the analysis you are making is an open system analysis. But for initial studies, normally we'll focus on closed system. What is a batch reactor, batch vessel. So if you can understand this closed system first, and then we'll go to the open system. Okay, next, about the properties. So what are the property we can classify into two categories. One is intensive, another is extensive. As the name indicates, extensive, it means it's about extent of the system. So always if you keep on add some contents, the value of that property is going to change. For example, the mass and volume. Mass and volume depends on the extent of the system. Whereas these properties like pressure, temperature, or density, specific volume, these are all not going to change if you measure at any point. So these values are going to be the same. Whereas this depends on the total size. If you split these into, nice example is here. So suppose you have a container like this and divide this container into two half, then the volume of these two half are simply dividing by half. Whereas the pressure, temperature, all this intensity property value remains as the same as that of the original container. So otherwise, simply anything per kg, per kg or per meter cube, these are all what is called as intensive properties. So the nice intensive property are the specific heat, specific energy, and for extensive property, all these energy quantities are joule, mass, volume. These are all extensive quantities. So getting this intensive quantity from the extensive is simply divide that extensive with mass or volume. You'll be getting these intensive properties. Sometimes this intensive multiplied by these moles or mass will be getting these extensive properties. Okay, I think great. Sometimes this terminology better to understand. And next thing is about state function and path functions. Now, certain property values depends only on the initial. Of course, all the thermodynamic property depends on the initial and final states. Of course, there are also other two quantities we deal with in chemical engineering, in thermodynamics, is work and heat. So the work and heat actually not property of the system. So that value is coming whenever there is a change happening. So for example, change from this 1 to 2, which is associated with this much amount of work. If the process is happening by this path, there is path of 1D, this is 1D, 1D2. If the process is following this path, then this is the work involved. Whereas if the process is following this 1C2, then the area under the PV curve, there is a work. Service work depends on the path in which the process is executed. Not only work, there is also heat as well. In what way heat is depending? Because there are, we know normally this heat, or as we used to write this Q equal to mCp delta T or mCv delta T. So when to take Cp and when to take Cv, that again depends on the nature of the process, that we'll see in the aspect of heat separately. So always all these thermodynamic properties, like all these energy quantities, simply they depends on the state. So always this internal energy depends only on the pressure and temperature at this state, corresponding to this state, and the internal energy at this point corresponding to the pressure temperature of this point. So it doesn't depend whether the process is following this way, or is whether it doesn't worry about the state, or is it need not, it doesn't depend on the process by which the state is arrived. Okay, whether the process may follow this path or this path, but the end values, or is a delta U, depends only on the this final and initial. Okay, next work. Work of expansion, work of contraction or compression. This is a very important thing in the case of closed system, as well as that the same thing will also be useful in flow system, say what is called a steady flow compression. So the work is actually force into displacement, and for our thing we'll say in terms of pressure and volume. There is pressure is force per unit area, and that area multiplied by distance is volume. So there is work equal to integral of P dV. Actually this P is the external pressure acting on the system. What is the external pressure acting on the system? Okay, we'll again come to the reversible process. At that time we'll see about how this external pressure is simply changing to P. Okay, we'll come to that. Service work is integral of PdV. Of course, the sign. What sign we have? Minus we have. So for the case of compression, what happens? dV will be negative. Or what is the meaning of compression? We are doing work on the system. That's why the system is getting compressed. So whatever the work added, now we are adding work to the system. The work added to the system will be coming as positive because dV is negative for a compression. No, dV refers to final minus initial, and final volume is lesser than the initial. So definitely dV is negative. So dV negative dV, this is negative quantity and this already negative. So work will be a positive quantity. Otherwise, we are taking this, whatever you add to the system, that will be coming as positive. And in the case of expansion, what happens? Expansion is dV is a positive quantity. So dV positive, so work will be coming as negative. Otherwise, the system is losing its energy by doing work on the surroundings. That's why this negative value is coming. Of course, these are all simply sign conventions, not to worry. Only the magnitude is important, but sometimes there will be a cyclic process and we need to account this work term properly. That will, by the way of doing problems related to this, we'll be understanding it more clearly. And as I said, heat is simply mCp delta T. Of course, this is for sensible heat changes. Of course, in the case of phase change, we'll be simply having m lambda. Okay, of course, m is also should be there. Okay, or is whatever the Q we are referring is per unit mass now. Okay, this integral of C dt or this C can have, it may be Cp or Cv. So what is the meaning of Cp, Cv? Specific heat at constant pressure and specific heat at constant volume. Otherwise, the definitions of specific heat, change in heat required to change the temperature by 1 degree at constant pressure. There is a specific heat at constant pressure, likewise specific heat at constant volume. And for gases, the Cp is always greater than Cv. Otherwise, we need to add more heat for a rise of temperature if the process to be carried out constant pressure. Okay, maybe we'll understand why this is to be more in the way of doing a problem. Of course, more detailed explanation will be available in the regular class. Okay, Cp is always higher than Cv for gases, but for liquids and solids, there is no much appreciable difference between Cp and Cv, because these liquids and solid, they doesn't show any expansion because of temperature, not much appreciable expansion. So that's why Cp is roughly equal to Cv for liquids and solids. So in the case of heat transfer requirement, we simply take this as Cp delta T, irrespective of whether the process is happening at constant pressure or constant volume, or without worrying about the nature of process, we are simply taking this Q simply by mCp delta T. This is possible. This is applicable only for this liquids and solids. Otherwise, wherever there is no change of volume with respect to temperature. So always Cp is always higher than Cv, because of course the more detail I will explain in the class, usual class. So what is the difference between Cp and Cv? Cp minus Cv equal to R. Of course, this is valid only for an ideal gas. Cp minus Cv equal to R only for ideal gas. Of course, there is a peculiar phenomena with water in the case of Cp and Cv. That also we'll discuss in the class. Please to mute yourself. Sorry, this also I have to do. Okay, thank you. Now, we need to know about the various kind of reversible processes. Okay, now we are writing this work as minus integral of PdV. Actually, the original definition is P external. For a reversible process, there is no appreciable pressure between the pressure difference. I think better, please, all of you mute yourself. Thank you. Maybe in the coming classes, we'll have a different version of Zoom so that there won't be any interruption at all. At least in the regular classes, we'll ensure that there is no interruption during the classes by the way of having this Zoom webinar. Okay. So this, what is the P external is now changing to pressure of the system. This is possible only for P external is equal to.
Sir, can you please make me as a host, so the co-host, so that I'll mute them.
Yes, madam, please take it. Okay.
Yes, sir, I've done. Thank you.
Yeah, sorry for the interruption for a while. Okay. Now coming back, this reversible process, as I said, P work refers to minus integral of P external into dV. This P external will be approximately equal to P, which is nothing but the pressure of the system. Only when P external, there is a difference between the pressure of the system and pressure of the external is very minimum, or is what is called as a reversible process. Only for reversible process, this P external and P of the system will be nearly equal. Otherwise, the system proceeds by very minimum driving force. That's why every state, every content of the fluid will be in a uniform state. These are all the assumptions we make so as to relate this pressure, volume, temperature, so that we can easily estimate the work involved in a process. This will be, of course, it will be estimating the maximum possible work or minimum required work. We can aim to that level. That's why actually the reversible process concept is introduced. So in the reversible process, P of the system, or is P external is simply equal to P of the system. So because on P of the system, we'll simply call it as P. And P will be relating in terms of TV and other thing. Okay. So P is referring to pressure of the system now. But original definition is pressure, external pressure. And for reversible process, pressure of the external is simply equal to pressure of the system. So we are simply dealing with minus W equal to minus PdV. Simple. We need not, we won't worry. As and when the process is said to be a reversible process, we'll simply take the P equal to pressure of the system. Okay, but if it is a if there is appreciable difference between the system pressure and surrounding pressure, you should take only the surrounding pressure into consideration. That is what is called as that is a irreversible process. Okay, at least in the calculation of work requirement for a closed system, definitely we should see whether the process is reversible or it corresponds to irreversible. So that and all you have to look into look in detail. That you can easily get to know by the statement like there is a external pressure. There will be such statements available. Okay, that we'll see with reference to a problem. Okay, what are the various reversible processes? Isobaric, that means P constant. Isochoric, which means V constant. In the case of isochoric process, the work is simply 0, right? And isothermal, isothermal means constant temperature. And adiabatic, of course, it is a reversible adiabatic. So what is the applicable for a reversible adiabatic? PV power gamma equal to constant. And polytropic process. It can be combination of any of these processes. So that is simply called as polytropic. The equation is similar to adiabatic. PV power delta equal to constant. Of course, we will again write these applicable equations in the first class chapter as well. Maybe. Now, let us read through the problem statement. Are we in a position to identify what sort of processes happen? I will read this problem. I will just to break from monotonous theory. Let us try to understand the problem and identify the answer. A piston cylinder arrangement as shown in the figure. So this is where piston cylinder arrangement is initially containing air at 150 kilopascal, or its pressure gauge is 150 kilopascal inside and 400 degrees Celsius. The arrangement is allowed to cool. That means by the way of some sort of arrangement, it is allowed to cool to the ambient temperature of 20 degrees Celsius. So initially the contents are at 400. It is going to a temperature of 20 degrees Celsius by the way of heat transfer. Okay. The cylinder walls has stops of negligible thickness. There is a stopper that can prevent the movement of the piston from moving down. Of course, piston will keep on coming down, and as and when it touches a stopper, it cannot further go down. Okay, this stopper is helping to arrest the movement. The volume cannot be reduced below this, lesser than that volume. Okay, the stops are 1 meter from the inner side of the base of the surface of the cylinder. At the initial state, the piston is resting. The piston is resting 1 meter above the stops. So this is a stop, and it is resting 1 meter above the stop. Okay, corresponding to initial condition, the piston is at 1 meter above the stop. Okay. Now, so what are the processes that will happen in sequence? What is the process going to happen? It's a cooling process. Initially at 400 degrees Celsius, it has to brought down to a temperature of 20 degrees Celsius. So there is a cooling process happening. There is a thing, natural. But there is also information about pressure. Initially, the pressure is 150 kilopascal. How is the pressure actually maintained? So pressure of the system and pressure of the surrounding has to be equal. What is called as the pressure of this pressure due to the weight of the piston is balanced by the opposing pressure due to the pressure of the air. So the this pressure, opposing pressure, is simply equal to the mg, which is the force, gravitational force of the piston, divided by the cross-sectional area. So this mg by a, that is remaining constant, no? Because this is the mass of the piston head, and g is a constant. That area is also a constant. So the pistons, the pressure exerted on the air by the piston weight is a constant. And how long it will be constant? It will keep on, as and when the cooling is happening, what will happen? We can always try to make use of this equation. This PV equal to RT. So what happens? Temperature is going down. And what happens to the pressure and volume? Pressure will remain constant because this, of course, the pressure depends on the weight of the this piston head. So this is remaining constant, so it will keep on. The pressure will remain constant, but once it touches, till it touches, the volume will keep on going down. Or PV is proportional to T. So T is decreasing. So V is decreasing in proportion to T. P is remaining constant till this part. After then, what happens? Then also the weight of the piston is the same. But what happens? Once a piston touches this point, okay, what happens? Further movement is arrested. So then the process happening after the piston touches this point is what is called as a constant volume process, because still the cooling is going to happen because there is a large change in temperature. Of course, that we can also estimate that and all. There is a different topic. So once it reaches this stopper, once the piston is reaching this stopper to the level of stopper, then the further process is going to happen at constant volume. So what are the process happening? Definitely you can see the initial process constant pressure. For the next thing is constant volume. So what is the option? Correct option? D is the correct option. Now, what is the need of this identification? So in the case of heat transfer requirement for this process of cooling, the cooling of the cylinder contents by the way of this kind of piston arrangement. Till this in this initial volume change, the process is a constant pressure process. So how do you calculate the heat? That is equal to Cp delta T. Whereas once it touches that stopper and further process is happening in constant volume, of course the pressure inside the air will be changing. Pressure of the air will be changing, but though there is a pressure difference between this and this, between the outside and inside, that cannot make any effect because the stopper is now preventing. So the process is happening at constant volume, but there is a cooling process in proportion to the temperature. There is a reduction of pressure of the air. So what is happening? Yeah, initially is constant pressure followed by constant volume. Otherwise, change in volume followed by change in pressure. So this is the thing. It cannot be constant volume throughout because definitely as and when the cooling is happening, piston will keep on come down. And it cannot be constant pressure throughout because as and when the piston touches this stopper, further process cannot happen at constant pressure because still the cooling is happening. That will make a reduction in temperature, but the volume is going to remain constant. Since the volume is remaining constant, only the pressure will decrease. Okay. Hope the explanation is good now. Maybe of course, this was a numerical problem. I slightly taken these aspects alone to identify the processes. This is a nice problem. Of course, this problem I have taken from this engineering sciences. Of course, engineering sciences is also is having this fluid mechanics, thermodynamics. So these are all nice topic to go through from the engineering sciences. Normally, this gate stream is taken by science graduates. Okay. Now let's go to the next. We finished 1/3 of our discussion, which is the basic aspects. Now the PVT behavior of pure components. In that, we need to initially know about these diagrams, namely pressure, temperature, volume, and pressure volume diagrams. So the pressure temperature diagram, of course, this diagram we used to learn from our school days itself. So what is it saying? Of course, it is a nice Y-shaped curve. No? This Y, simply I can make a Y. Simply Y. Okay. So this Y is this we also call it as a phase diagram, which is PT diagram. PT diagram. This first line is a sublimation, or solid to vapor, direct change from solid to vapor, and after this triple point, we have this solid to liquid change possible, and liquid to vapor. So this liquid to vapor, we know this vaporization, that is a usual. We normally do any chemical process in this area. Even if you have solid also, we'll convert into liquid and we'll carry out the process, or we'll try to raise the temperature and make it to liquid, and liquid to vapor. These are all always in fluid state only. We are doing our chemical processes. Maybe that video also people can mute, or this. Okay. Now, so what is the importance of this diagram? Okay. So there are two lines shown here. This line, what is the meaning of this line? Of course, the melting, every line is having a positive slope. But only for this dashed line, we see there is a negative slope. So for this, this is a peculiar case applicable for substances that expand on freezing. So the nice example is water. Of course, water is such a peculiar substance. Otherwise, every substance normally from liquid to solid, it contracts. There is a reduction of volume. But only for water, of course, it's a God's creation. For water, there is an expansion of this volume. Otherwise, the solid is tending to float over the liquid. Of course, it is not this much change. There is only appreciable, so very light negative slope, but still, okay. Just to show it in the diagram, we are representing in a very bigger way. Okay, so okay, what is important? Everywhere dp by dt is positive only for these substances that expand on freezing. Otherwise, the systems as like water, we have a negative slope. That is a learning from this thing. And after this critical point, simply it is gas. And next thing, okay, TV diagram. This is the easiest diagram I consider. It can be easily understood. So, of course, the bell-shaped curve corresponds to the saturation curve. To the left of this curve, we have this. This is saturated liquid, and this is saturated vapor. And to the left of the saturated liquid, we have subcooled liquid, and to the right, we have superheated vapor, and this is a gaseous state. And in thermodynamics, we have simply this pressure, volume, temperature. These are the three states. Three variables, important variable. And out of these, we'll be mostly dealing with pressure, temperature, because these two properties can be easily measured. No? How do you measure? Simply put a pressure gauge or temperature gauge, measure it, or thermometer, pressure or manometer. These also giving the indications of pressure and temperature. Whereas volume of the system, it's creating a lot of problems. Or is for flow system, we cannot easily measure volume easily. Even for closed system also, volume is again a function of temperature. Service, it creates a lot of difficulty. So this temperature and pressure are the essential variables that we'll be using in our thermodynamics. Okay, coming to the discussion on this diagram, we have, of course, since temperature and volume are in the axis, so we'll be having pressure at constant pressure, how the diagram will look like. At constant pressure, say, let us consider the state of 1 bar. At 1 bar, initially water is at say 20 degrees Celsius. We are adding heat and temperature is going to 100 degrees Celsius. At that point, we'll see the first vapor coming out. So that is what is called a saturated liquid. And further addition of heat creates vapor in the relevant proportions. And this is a point at which entire liquid is turning to vapor. So what is called as at this point we have no liquid presence. That is, the quality of this fluid is 100% vapor. And further addition of heat simply heats up the vapor, what is called as superheated vapor. So this is corresponding to a pressure of corresponding to one pressure. What will be the another pressure line? We'll be having simply this thing. And of course, during this phase change, the process is happening at constant pressure and temperature. So simply a horizontal line. So of course, the horizontal line width is keep on decreasing, and it is merging to a point at the critical point. Okay, a lot of discussion can be made on this thing that we'll see with reference to problems. Next thing about pressure volume diagram. So pressure volume diagram, of course, this also has good. We need to discuss about this. So pressure volume diagram, in what way? Because these curves, no, what is called as isotherms. No? Pressure volume diagram, these are all constant temperature lines. So the constant temperature lines, of course, has a sudden in the phase change, we'll be having, in addition to constant pressure, there is a constant temperature. Otherwise, temperature will be constant. So of course, this is a constant temperature line. In addition to temperature remaining constant, pressure is also remaining constant during the phase change. Now, we have these constant temperature lines in the increasing temperatures. At the critical point, this horizontal line or this line is simply turning to a point. Of course, this critical point is at the critical point. There is a condition that we'll see in the next slide. So what is called as, this is a saddle point. Why it is called a saddle point? There is a sudden change in slope at the saddle point. Okay, we'll discuss later. Then what is applicable at the critical point. So at this point, the first derivative, which is nothing but dou P by dou V at constant temperature, as well as dou square P by dou V square, both are equal to 0. Or is this condition will be used to evaluate the constants of the equations of state. So is this point, because this point is valid at the critical, or is this condition is to be valid at the critical point. So using that condition, we are actually evaluating the parameters like van der Waals parameters. What are the parameters? A, B, and like that for Redlich-Kwong. So whatever the these parameters of the models, cubic equation models, normally we evaluate using these conditions at the critical point. Okay. So before before saying about the models, the first and is the best model, no? Nice model we'll use in our thermodynamics. Not only thermodynamics, all our chemical engineering, everywhere. Most of the time we'll be using this PV equal to RT, or even though if it is not a gaseous state, we'll be still using R in most of our property predictions. So what is the significance of this equation? This R is again based on this ideal gas equation. So what is the significance of that R? So for that, we need to know about this model equation, ideal gas equation, very simple equation, PV equal to RT. So what it says, of course, this temperature is to be in Kelvin. And here, and at what conditions any gas can be considered, any component can be considered as ideal gas. Of course, any component, even a gold, which is a solid, can be brought down to ideal gas state. But what is the pressure temperature condition? Pressure temperature conditions correspond for making this ideal gas equation to apply is nothing but your low density state. Or is density, how do you find? Rho equal to Pm by RT, which says that for low density means this density to be lower, pressure should be lower, or temperature should be higher. So higher the temperature and lower the pressure. But by what value? So we'll be again referring with reference to the critical pressure and critical temperature. But I will write here so that is critical what is it? Critical pressure. 1 minute. So what is the meaning of critical pressure, critical temperature? Of course, that I am not going to discuss. So with reference to the critical pressure, there is a state what is called as reduced pressure. Otherwise, if the pressure is less than PC and temperature is greater than TC, much lesser and much greater, at that condition, any component will have a low density. Rho is Pm by RT. So this T and P has to validate this condition, or they have to match this requirement. Then any component can be brought down to ideal gas state. And at that condition, at that state, this equation is valid. PV equal to RT. Of course, V refers to molar volume, and R is the universal gas constant. How do you find R? Many times people struggle in getting the value of R. There is nothing difficulty. Simply, if you remember this one point, or is 1 atmosphere and a temperature of 273 Kelvin. At 1 atmosphere and 273 Kelvin, any ideal gas, any gas will occupy a volume of, of course, any ideal gas only. Any ideal gas will occupy a volume of 22.4 liter per mole. So if you use these 4 data, you can evaluate the value of R. Okay, sometime we'll be pressure having in Newton per meter square, and this liter will be in terms of meter cube, and mole maybe in K mole. Accordingly, you will be having the variety of values of R, but all are referring to the same. The units are only differing. So the requirement for evaluating you need to know only this one value, 1 atmosphere and 273 Kelvin. That is 1 atmosphere and 0 degrees Celsius. No, of course, we need to use the temperature in Kelvin. So 1 atmosphere and 273 Kelvin. Any ideal gas occupy a volume of 22 liter for a mole. Mole refers to simply gram mole. That is 22.4 meter cube per K mole. And this 1 atmosphere, you can also write it as 760 mm of Hg or 1.01325 bar. So you can use variety of such thing. Okay. and to evaluate, or else you can report this R in variety of ways. Okay, this and all I will remove and not necessary, so that I will use this later. Okay, coming to the next one. So of course, ideal gas equation is not always valid. We are it is having deviations. Sometimes these cubic equations are needed, because what is the need of this cubic equation? Or is ideal gas equation is valid in these regions, whereas when we are dealing with a state lesser than the critical point, we need to use these other equations of state. The simplest equation next to ideal gas equation is van der Waals equation, which is P plus A by V square into V minus B. So this A and B are the fitting parameters of this van der Waals model. Of course, if you expand, you'll be having a cubic term for V. Of course, solving this cubic equation is again involving trial and error, which is slightly not so easier. Next thing is about compressibility factor. How to evaluate A and B using this dou P by dou V and dou square P by dou V square at TC. So that is also a topic. We can also write this A and B in terms of TCPC. Better to memorize that equation as well. Okay, that we'll see in the coming classes. And deviation from ideal gas, the behavior is also represented in terms of compressibility factor. So actually, what is this? RT by P is simply, if you can also write this as Z equal to V by RT by P. This RT by P is nothing but V from ideal gas equation. Otherwise, Z, you can also write it as V by VIG. Otherwise, the actual volume of the gas and volume predicted by ideal gas equation. So there is also another meaning for this equation. So volume estimate, the volume, actual volume by volume estimated from the ideal gas equation may not be the equal. It will be equal whenever the pressure is low and temperature is higher in comparison to their critical pressure and critical temperatures. Okay, Z can have value equal to 0. Of course, it is equal to 1 for ideal gas. Value can be lesser than 1 or greater than 1 as well. Okay, this deviation from indicates the deviation from ideal gas behavior, ideal gas conditions. Okay, next model about equations of state is virial equations. Of course, we'll be writing this Z as a polynomial of V or P. Of course, polynomial of V means not simply P V square, PV, it is P by V, because this is actually, yeah, let us not worry. So this Z is 1 plus P by V plus C by V square. Normally we'll limit to these two form, because this itself will end up with a cubic equation. If you include more terms, then you'll be having, what is it, fourth order polynomial, so which is not so easy to evaluate. So normally this is one parameter, this is a 2 parameter, this is a 3 parameter. So this 3 parameter model is normally used. There is 3 coefficients. The first coefficient is simply 1, the second coefficient is B, and third coefficient is C. So using this form of virial equation is quite commonly used. It can also be written in terms of a pressure series. Is that equal to 1 plus P dash P, or is this B and this B dash are different? Okay, this we'll see later in a problem solving. And this Z can be obtained from the table of reduced pressure and reduced temperatures. Otherwise, this for various values of reduced pressure and reduced temperature, we can get the Z available in the table. What is the meaning of TR, PR? Of course, no? TR, PR. That is PR is P by PC. This is simply dimensionless, making it dimensionless form. PR is a dimensionless pressure. No? TR is dimensionless temperature, T by TC. Of course, everything, this is T is in absolute temperatures. Okay, that should be taken into mind. Next, still the 2 parameter model is not fitting well to most of the components. So we go for 3 parameter model, including a term what is called as omega is eccentric factor. This eccentric factor is equal to 0 for what is called as simple fluids, namely argon, xenon, this rare gases. For the rare gases, this omega value is 0, whereas for other thing, it's having some value. The omega value is also available for the variety of components. Okay. So otherwise, we'll be having a table of Z0 and Z1 as a function of TRPR. Using that table values, we'll be getting this Z0 and Z1 for a given TRPR, and this Z0 and Z0 plus the omega into Z1 will give you the value of Z. So once the Z is available, we can get to know this volume because Z equal to PV by RT. Okay, fine. So another about 15 minutes left. So before going to the first law, we'll see a relevant problem to this equation of state. If 1 mole of H2 gas occupies a rigid container, so always we have a rigid container with a capacity of 1000 liters, as we know the volume now. Okay, always what are all available? So 1 mole and volume is 1000 liter. Okay. Now temperature is changing from 27 to 37. So temperature is changing from, there is a change of 20 degrees Celsius. Sorry, 10 degrees. Delta T is changing by 10 degrees Celsius or 10 Kelvin. 10 Kelvin. 10 degrees Celsius change and 10 Kelvin change are the same, right? Now, it is simply the change. So what is the need of that? Okay, we'll see. We are asked to find the change in pressure. That is for the change in temperature of 10 K. What is the change in pressure? So how to find that? Simply what is happening in the process, or is the rigid container? No? It's helpful because for a rigid container, volume is remaining constant. Or is the container cannot expand or contract. No? So what is happening is that of course there is a heating process. There is an increase of temperature by 10 degrees Celsius, and what is the corresponding pressure increase? So we can write this PV equal to RT, and V is remaining constant. V is constant, so which gives pressure is proportional to T, or is delta P is proportional to. Can we take that way, or is we can initially first find the pressure? Or is delta T? Yeah, delta T also will be proportional to delta, or is delta P will be proportional to delta T. Is that possible? Yeah, correct. Or is this is temperature, or is volume is remaining constant? So only pressure changes. So we can find this. Okay, this workout maybe I will send you the. I'll give you the answer. Maybe you can work it out. So we have only another about 15 minutes maximum left. We'll see the next one. The first law. Of course, first law, we know simply it is energy balance statement. So energy change of the system and energy change of the surroundings, total energy change is equal to 0. There is no system plus surrounding together is the universe. So total energy of the universe is remaining constant. That's a statement. So energy change of the surroundings, it is energy change between the system and surroundings is happening in the way of heat and work interactions. So we'll write like the energy change for a system that is happening by the way of heat and work interactions. And most of the time we'll be having this dealing with processes wherein which there is no kinetic energy or potential energy change. So you'll be having simply delta U equal to Q plus W. So what is this is a simplest statement. But sometime we'll be having this Q minus W. So when to take Q minus W, always in our thermodynamic treatment, we are going to have this simplest form, delta U equal to Q plus W. So of course, it has a kind of sign convention. So what is a sign convention? Always, we follow the convention. Of course, our Smith and Wallace also follows the same convention. Whatever is added to the system is taken as positive. So whether it is heat added or work added, both are taken as the same way. If you add heat to the system, its energy is going to rise. If you also add work to the system, it is also going to raise the energy of the system. Whereas in mechanical based groups, they will be having the other equation Q minus W. Otherwise, for them, heat added to the system is positive, and work done by the system is positive because they are interested in getting to know the maximum work possible from a process. For the case of this power cycles, So that's why they have this Q minus W. Of course, that definition of W equal to simply integral of PD. So otherwise, that way they are adjusting that. So otherwise, the first law statement is the same. It is simply the heat and work interaction. That is, energy change of the system is happening in the way of heat and work interactions. Here we'll be having, in our treatment, we are simply taking whatever is added to the system is positive. So if you add heat or work, system's energy is going to rise. Whereas in mechanical treatment, books and all, we'll be seeing heat added to the system is positive, work done by the system is positive. So to take that, we'll need to have Q minus W as the equation for delta U. Okay. Then the another property, of course, internal energy is one thermodynamic property. The another property, of course, the enthalpy, which is very much useful for flow systems. Flow systems mean all our thermodynamic, all our continuous processes. So in that cases, instead of this using U, it will be very convenient to use this enthalpy. So enthalpy is actually U plus the another quantity what is called as PV. The PV is the P and V, which is also a multiplication of PV will end up with the energy term. So there is a flow energy. So whenever there is a flow, or there is open system, we have a flow. So for this open system, this in addition to U, there will be also this PV changes. So U plus PV change together is considered as enthalpy change. So enthalpy definition is U plus PV. Okay. So everywhere we are now dealing in terms of per mass. So we want to have total enthalpy change. This will be having UT like PVT. The superscript is PVT refers to this total volume. Okay, not to worry now. So the energy changes for an ideal gas. Of course, many times we are simply restricting ourselves to ideal gas. Or if we can get to know the changes happening in ideal gas, then we can also extend to other system. Or this ideal gas will give a lot of ideas. Say, otherwise, any component can be brought to ideal gas state at low pressure conditions, at low density conditions. What is it? The low pressure and high density, high temperature. So otherwise, this ideal gas, better to know about these changes happening for an ideal gas. So for an ideal gas, this du is simply given by Cv delta T, dH is given by Cp delta T. Otherwise, this is heat addition at constant volume, heat addition at constant pressure. Whereas du corresponds to heat addition at constant volume, dH corresponds to heat addition at constant pressure. Of course, already we said this Cp minus Cv equal to R for an ideal gas. Only for ideal gas, the specific heat at constant pressure is higher than specific heat at constant volume. The difference is simply universal gas constant. So as I said, this the relations we can write for this various processes with ideal gas. For isothermal process, PV equal to constant, or is delta equal to 1. What is that? PV equal to constant. Why that is coming? Because PV equal to RT. For isothermal process, T is remaining constant. That's why PV equal to constant. Okay. And for isobaric, of course, P is remaining constant. So there is V to the power del 0. To make this term not there. So we'll be having V power 0. That is valid for isobaric. And for isochoric, V to the power infinity. P V power infinity equal to constant. And reversible adiabatic, for which PV power gamma equal to constant. Gamma is nothing but the ratio of specific heats. Cp by Cv. For air, it is 1.4. So these are all known to us. And cyclic process. So what is going to be a cyclic process? Of course, there is a fluid which is undergoing changes and again coming back to the same state. Of course, this is very applicable for our boiler system. What is a power plant system? So there is water inflow. Water is going to the boiler, again going to the turbine, again going to the condenser and back to the boiler. So the water is in cyclic process, for which the total internal energy change of the water is simply 0. Not only internal energy change, it's also for any other energy quantities, of course, this enthalpy change is 0, what we have seen now. So internal energy change and enthalpy change, of course, these are all the state functions. What is the meaning of state? It depends on the state. It's changing from one state to other state, again coming back to the state. So internal energy change, enthalpy change are simply zero. For a cyclic process, the change in state, it is coming to the same state. So delta of that processes will be simply zero. Delta of that properties will be simply zero. Okay. Yeah, first law for open system. Of course, from the same first law equation, already we have this delta U equal to Q plus W. Q can be broken into two quantities. One is a flow energy, another is soft work. Flow work and soft work. The flow work, already we know this flow work is PV, and soft work, it can be through the way of there is a agitation or compression. So these are all coming in the way of soft work. So from the definition of enthalpy, so this delta U and flow terms will be combined. So to get delta H. So as like our delta U equal to Q plus W, for flow process also we have a same exactly similar, but instead of W, this is W. Yes. So this W or is W of this closed system is work of expansion or compression, whereas here this WS is the soft work, which is in the way of agitator or reciprocating compressor. So these are all work of soft work or a turbine. Okay. Yeah. Now let us try to answer this question. I think with this, in another about a few minutes, we'll be ending up. During a non-flow thermodynamic process. So what is the meaning of non-flow thermodynamic process? A closed system. Executed by a perfect gas, the heat interaction is equal to work interaction. So always we get the Q and W are the same. So for which process this is applicable? Otherwise, we know the equation delta U equal to Q plus W or minus W. Okay, so here W and Q are said to be equal. So in that case, we can use this equation Q minus W. Of course, this question I have taken from a mechanical engineering thing. So work interaction, or is the delta Q and is magnitude of Q. Or is you can write like absolute. This way is correct, no? So otherwise, the work interaction and heat interactions are the same. So for which process this is applicable? So that means this will lead to is your delta U equal to Q minus W. So W and Q are the same, which is applicable for delta U equal to 0. So when is this delta U will be 0? Simply it is possible only for isothermal process. Now why it is for isothermal process? For isothermal process, delta U equal to, of course, delta U equal to simply CV delta T. For isothermal process, delta T is equal to 0. So delta U also 0. So this is the answer. Okay, this kind of problems we will try to solve in the classes. Of course, there is another trial class I am putting on this coming Sunday. Coming Sunday from 8 to 11, we'll try to see at least some good number of problems covering these three chapters of thermodynamics. Okay, with this we are coming to the end. Of course, I will also show you, of course, you can reach us through these websites, msubbu.academy, which is the LMS platform of our materials, and msubbu.in is having a lot of free contents, and again, it's a payment collection site for this msubbu academy. That is, once you create a login and purchase the courses, you'll be automatically taken to msubbu.academy. Whatever the ID you have is applicable for msubbu.academy as well. So both are sharing the same user ID data, and we are reachable through this learn at msubbu academy, or you can also reach through me by WhatsApping this number. And for any sales related queries, you can also reach to another number 9840102079, through which you can reach regarding any sales related aspects of this msubbu academy. Now, let me give you a idea about my courses, so that those who haven't already used my site, I'll use a student ID. Yeah, better I'll use a student ID. 1 minute. Yeah, this is corresponding to, yeah. 1 minute. So better to show you the features of a student. Of course, hereafter I'm going to give only about my site features. It will also be helping you to know about what are all there in my website, no? Because many times you would have thought about it and you would have been purchased any courses. In that case, you can simply try to purchase one course so that you'll feel 1 minute. Okay, sorry, it's creating some problem. Camera covered. Okay. Yeah, as and when you log in, you'll be going taken to the dashboard, wherein which your courses, whatever you have subscribed, or whatever the courses you have enrolled will be listed. Here, for example, thermodynamics course. So whatever we have seen are already there in this book. In this, of course, these are all simply my book contents in a nice interactive way. In addition to the book contents, I am also putting in a lot of latest thing, and we have a highly interactive feature. So here in which I put up a checklist so that you can also uh, directly go to there. Say for example, this checklist. So here you'll be taken to the relevant page, or here also you can add some comments so that you can, it will be useful for your later reference. Coming to the first, we'll see about the text contents. Say for example, these are all the text contents. Say for example, already as I said, no, this table is already there in this book, in this online course. Of course, the book content in a very different way. So here the nice feature is actually this tagging. So this tagging is very helpful so that you can go get more detailed aspects relevant to a tag. Say for example, these are all the relevant items. So every question is also, every material is having a tagging, or what is called as keyword. So this keyword index is very helpful so that you can study a concept in detail. Say for example, activities coefficient is having a lot of contents. Sorry, what are all the materials relevant to activity coefficient? They are listed. Say again, I need to say one point. Say if the size of this tag is bigger, which indicates there are more materials on that. For example, entropy change is bigger, whereas the other site like heat pump is smaller, which means heat pump is having lesser questions in corresponding to the what is it, ideal gas. So there is bigger the size indicates more number of materials. Otherwise, which is the most often asked topic. So there is simply, if you want to study, you can simply go through this work term. Work is having bigger size, which indicates work is a most asked thing, and isothermal process. Okay, by the way, you can go through, and suppose you want to study this materials, say like this kind of questions are there. Initially, you'll be having only this question alone available, and you can select anyone, and if you have worked out, you can choose the correct option. Otherwise, also you'll be getting with a solution. These fonts are quite nice fonts. You can see in any device, any electronic device. So you can use it in your mobile, or in computer, or in your laptop, or your iPad, or even in your computer, smart computer. Sorry, smart TVs. Smart TV also you can access in a bigger font. So as I said, everywhere we have this keyword tagging that will be very helpful. Again, coming back to the homepage of that course, here a lot of questions are given for practice, which means questions are given with only answers, answer key, and a lot of video contents we are putting. So as and when I'm finding something interesting, I'm trying to give that content by the way of video explanation. Most of the time it is simply recorded content. So this and all you can go through sometime yourself. Some videos I am posting in the public domain, namely YouTube. Of course, most of the contents I am putting it in my own video streaming server. So which is unique, available only to the subscribers. And a lot of other features, like you can publicly put a comment or you can message the teacher. Of course, wherever you are there, you can simply send a message. Suppose any of the topic is not easily understandable by you, you can simply send a message. So whatever you send will be also having having the reference to that page, so that the teacher can easily identify in what context you are making that question, and the teacher will be in turn replying. As of now, I am the teacher for most of the courses. I'm also having a panel of teachers, or my teacher colleagues are available. I will be attaching them also to the every courses. Okay, now coming back to the thermodynamics course again. So I can show you the otherwise the interesting feature. This kind of, or else you can take up any number of quizzes so as to check where you stand. So these are all self-assessment quizzes. Most of the questions are having solutions. How to go to the solution? Of course, there is a keyword, no key XC 2013 E4, which means the question is taken from XC 2013, or is Engineering Sciences 2013 year, and exact question number is also put up. This you can simply copy and search in the this course page. You'll be taken to that page correct directly. Okay, and you can take any number of quiz any number of times. I am keep on adding contents, and every week also put up some kind of revision problems, or just to ask you where you stand, or just to ask remind you, or about the new materials. We are putting such contents, and there are progress for indicating the activity completion, and you can also get to know about your grade. So there are always variety of features are there. These are all much more better features than a usual print book. So because of these nice features, in the recent time we haven't made the print book available. Of course, just to encourage this usage of online courses. All these online courses, or this entire chemical engineering bundle, we are giving it at a price of about 4,300 plus 18% GST. That is for 15-month access, whereas one can also get for a month access, 1 month access also available. Say for example, everywhere we are putting 1 month access and 15-month access. 1 month access will be only 1/3 of the 15-month access, just to encourage for a longer duration. Or is a longer the duration, the prices are reduced. Okay, these are all something about my course materials, and also we are going to conduct these trial gate classes, full-fledged classes. So already about 10 people have joined here, and we are going to conduct the classes from the coming Tuesday. Yeah, at least in about 3-4 days we are going to start the full-fledged online coaching class. So that will be more interactive, and we are restricting to only 20 people. And it is not simply this lecturing in the classes. I'll be giving a lot of exercises from this online platform. Let me show you that full-fledged content. Yeah, okay, that I will show you in the coming class. Let's not spend time. Already taken 7 minutes of your extra time. Okay, so these are all the nice features. One can easily access these materials simply by making a payment of only about 1,300 for 1 month access, or 4,300 for 15-month access, or even for if you want 1 day access. That is, you want to see what is really there. For 1 day access to this typical course, we are putting it only about 47 rupees, which is 24-hour access. Okay, these are all for you about our courses and coaching. So one more trail class is there, which is on this Sunday. Please join from Sunday 8 to 11. Okay, so these details also there. Of course, we will send you the link details and all. Okay, thanks for your patient listening. We will have more interactive contents in the coming Sunday session, because this is a problem solving session. Otherwise, I will be discussing more. It will be also kind of interactive session. Thank you all for your patient listening and interaction in the classes. Thank you.